let's take an overview of the ketogenic diet. Our normal diet, if we talk about our normal diet is our normal diet consists of more carbohydrate. It contains moderate protein and moderate fat. And while the ketogenic diet, if we talk about the ketogenic diet, as we discussed earlier, that ketogenic diet is very high in fat, it's moderate in protein, and very low in carbohydrate. So our body metabolism is normally running on high carbohydrate. When we take very low carbohydrate in our diet, then the body in the start but will use stored glycogen as an energy source. But when the glycogen has been depleted, then the body will try to find any other way, any other source of energy. In that case, body will use fat as an energy source. And so body metabolism is shifting under the influence of ketogenic diet. Body metabolism is shifting from carbohydrate metabolism towards the fat. So that diet shifts the body metabolism from carbohydrate towards the fat. But that is not so easy. It's very complex. There are very complex mechanisms behind the whole procedure, that how the body shifts from carbohydrate metabolism towards the fat, towards the ketosis. So how this ketosis occur? We just take an overview that how this happens. When body is on very low carbohydrate diet, in that case, a few hormonal changes come. So in that case, insulin level will drop and counter regulatory hormones level will increase. The counter regulatory hormones, number one is glucagon, and then it also includes catecholamines like epinephrine, norepinephrine, cortisol, and growth hormones. Let's discuss what is the normal function of insulin. Insulin, actually, it's an anabolic hormone. It stores glucose in the form of glycogen, and it stores free fatty acids in the form of triglycerides. But these counter-regulatory hormones are different, are opposite to the insulin functions. Glucagon and these other regulatory or counter-regulatory hormones, these are actually catabolic hormones. Insulin is an anabolic hormone. It converts glucose into glycogen and free fatty acids into triglycerides. While these hormones, they actually convert triglyceride back into free fatty acid and glucagon back into the glucose. So let's just take an overview. First, we take an overview of insulin, and then we discuss about the glucagon also. And just take overview that how this ketogenic diet lead to the synthesis of ketone bodies. Suppose it's an adipose tissue. Let's make it a little bit bigger. and it's the blood circulation. Insulin, as we discussed, that insulin under the influence of ketogenic diet, level of insulin decrease. But what's the normal function of insulin? That insulin stores glucose in the form of glycogen and it also stores free fatty acids in the form of triglycerides. So it's an adipose tissue. Insulin, so it's the insulin receptor. It's an insulin receptor. Insulin bind with its receptor. As a result, series of signaling pathways start and insulin activating enzyme and that enzyme name is lipoprotein lipase. When the insulin bind with its receptor on the adipose tissue, a series of signaling pathways starts. As a result, it activates enzyme in the blood circulation, not in the adipose cell. It actually activate enzyme in the blood circulation that is bind with endothelial cell, and that enzyme is the lipoprotein lipase. This lipoprotein lipase actually it's break down triglycerides. As discussed, it break down triglycerides present in the blood circulation in the form of VLDL and in the chylomicron. Both VLDL and chylomicron both are packed with the triglycerides, but the origin of both are different. VLDL also is rich in triglyceride. Chylomicron also contain triglyceride. Both are the lipoproteins. VLDL contain triglyceride, but this triglyceride synthesized in the liver. Liver synthesize this triglyceride and then pack in the VLDL and then transport into the blood. Chylomicron also contain triglycerides, but triglyceride present in the chylomicron, its origin is it's not synthesized in our body. It's actually coming from diet. The diet we take, fat diet that we take, and that triglyceride that we take through diet actually pack into the chylomicron and then transport into the blood. Now, lipoprotein lipase, what will do? Lipoprotein lipase will break down the triglycerides present in both VLDL and chylomicron. So lipoprotein lipase, what the lipoprotein will do? It will break down the triglycerides and present in both chylomicron and VLDL and convert it into the free fatty acids and glycerol. These are actually free fatty acids. I just draw it in. These are free fatty acids and it's a glycerol. Now these free fatty acids then transported into the adipose tissue, and glycerol will go back into the liver. So listen again, how insulin break down the triglycerides present in the blood circulation that are coming from liver and GI tract, break down into the free fatty acids and glycerol, and then these free fatty acids are then transported, then go back into the adipose cells, and glycerol that is comes after the breakdown of triglyceride that actually go back into the liver. No, insulin also did another function, that insulin also through a series of signaling pathway increase the transport of GLUT4. increase the transport of specific glucose transporters. Their transporters are GLUT4. Insulin increase the transport of GLUT4 from the cytoplasmic space into the membrane. And from through these transporters, glucose from the blood. So these transporters, glucose from the blood enter into the adipose cell and it's converted into the glycerol. So insulin is doing two functions. Here, the number one, insulin activate the enzyme that is lipoprotein lipase present in the blood circulation, and this lipoprotein lipase break down triglycerides present in VLDL and chylomicron and convert it into the free fatty acids and glycerol. Then these free fatty acids enter into the adipose tissue and glycerol go back into the liver. So in other ways, insulin also increase the transport of GLUT4 transporters, also transport that it increase the uptake of glucose from the blood into the cell, into the adipose cells, by increasing the number of glucose transporters into the membrane, in the cell membrane. Now, as more glucose will enter through the blood, from the blood into the adipose cell, now these glycerol and free fatty acid then combine together and they synthesize triglycerides. Now, as we discussed earlier that insulin is an anabolic hormone. It stores free fatty acids in the form of triglycerides. So let's discuss about the glucagon. What the glucagon do? Glucagon also bind with its receptor. Glucagon will also bind with its receptor. So and the receptor is 7-pass receptor. It binds with its receptor, and again a series of signaling pathways will start, and it activates enzyme, another enzyme. That enzyme is the hormone sensitive lipase enzyme. So both insulin and glucagon both are activating lipase enzyme, and the function of both enzyme is same, but location of activation is different. Insulin is activating the lipase enzyme, that is the lipoprotein lipase, in the blood circulation, but glucagon is activating enzyme that is the hormone sensitive lipase, but it's activating in the adipose cell. Now this hormone sensitive lipase will act on triglyceride and again break down into the free fatty acids and glycerol. Now these free fatty acids will be transported into the blood circulation, and from the blood circulation it will be transported to the other body tissues, and the body will use these free fatty acids as an energy source. So these triglycerides and the free fatty acid and glycerol will transported into the blood circulation. This is a free fatty acid and it's a glycerol. Now these free fatty acids and glycerol, these will be transported into the different body tissues, and body tissues will use this as an energy source. Now glycerol is transported to the other body tissues alone. You don't need any other assistance of any transporter. But free fatty acid is not a water soluble. Glycerol is a water soluble, it can transport alone, but it needs the assistance of any other transporter. So that transporter is protein, that is a albumin. Albumin is a protein, suppose it's an albumin. It binds with this protein. Free fatty acids bind with this protein, and then it will be transported to the other body tissues. And so I draw one body cell of any body tissue here. It will be transferred to the all body tissues, but except few. We discuss it later that what are those few two body tissues that can't use free fatty acids as an energy source. So these free fatty acids. So it's I draw a cell, and here's some mitochondria. It's a mitochondria. These free fatty acids will be transported to the other body tissues through the protein albumin. So and this transport free fatty acids into the cell, and then it's entered into the mitochondria of the other body tissue. In the mitochondria, free fatty acids converted into the acetyl CoA, and acetyl CoA then enter into the TCA cycle, and from the TCA cycle ATP is generated. So in short, that free fatty acid generate ATP in the mitochondria. I actually enter into the go to that tissue, enter into the cell and the mitochondria of that cell, and through the in the mitochondria ATP is generated through the TCS cycle. Actually, first it is converted fatty acid is converted into the acetyl CoA through beta oxidation. Its breakdown, fatty acids breakdown occur in the mitochondria through the beta oxidation, and it's converted to the acetyl CoA, and acetyl CoA then enter into TC cycle, and from the TC cycle energy is generated and the body use that energy. But not all the body tissues can't, no all body tissues can't use these free fatty acids. No, number one is red blood cell. Red blood cells can't use free fatty acids as an energy source. The reason is the red blood cells do not have mitochondria, because free fatty acids breakdown occur in the mitochondria. So mitochondria is not present in the RBCs. So the free fatty acids, RBCs can't use free fatty acids as an energy source. The other body tissue is our central nervous system. Our central nervous system can't use free fatty acid as an energy source, and the reason is albumin can't cross the blood-brain barrier. That's why our central nervous system can't use free fatty acid as an energy source. So our point is, actually our main point is how this ketogenic diet lead to the synthesis of ketone bodies. No, we have maximum of our we have the discussion. We have done our maximum discussion that how insulin and glucagon actually working. That insulin increase stored glucose free and free fatty acid as in the adipose tissue in the form of triglycerides, and glucagon actually do the catabolic. It's a catabolic hormone, and it break down triglyceride stored in the adipose tissue into the free fatty acid and glycerol, and then body use that free fatty acid as an energy source. But what happened when the body is on the ketogenic diet? When the body is on the ketogenic diet, in that case, insulin level decrease, and the level of counter-regulatory hormones like glucagon, like catecholamines, epinephrine, norepinephrine, cortisol, growth hormone, their level increase. And what these hormones will do? these hormones will start the lipolysis. They will start breaking down the triglycerides stored in the adipose tissue, in the free fatty acids, and in the glycerol. When a lot of when a large number of free fatty acids through the blood circulation enter into the target tissues, then the free fatty acid will be converted, instead of converted to the acetyl CoA first, and then instead of going into the TCA cycle, it will go into the any other cycle. It will not go into the TCA cycle due to massive, due to large number of lipolysis, due to huge lipolysis, due to increased senses of free fatty acids. As the result, in that case, acetyl CoA will not enter into the TCA cycle. It will go into another cycle, and that's the ketogenesis. But this ketogenesis do not occur in all the body tissues. Point is this ketogenesis do not occur in all the body tissues. It occurs only in one tissue, that is the liver. Ketogenesis occur only in one body tissue, that is the liver. It's a liver spot, and it's a mitochondria. Free fatty acid enter, as in other body tissues, free fatty acid enter into the mitochondria. These free fatty acids enter into mitochondria, and the mitochondria, it through beta oxidation, it will be converted into the acetyl CoA through beta oxidation. It will be converted into the acetyl CoA, and acetyl CoA then enter into TCA cycle. TCA cycle or Krebs cycle, and ATP is generated. But what happened here? When there is a massive production, when there is a massive lipolysis, when the body is on ketogenic diet, when the insulin level decrease and the counter-regulatory hormones level increase, at that time what will happen? When the level of counter-regulatory hormone will increase, lipolysis will increase, fatty acid breakdown, fatty acid synthesis will increase, and the more fatty acid will be transferred through the blood circulation, transported into the liver. In that case, this acetyl CoA, instead of going into the TCA cycle, it will enter into another pathway. And that pathway is ketogenesis. Acetyl CoA then synthesize ketone bodies. Instead of entering into the TCA cycle, it will synthesize ketone bodies. No, then the ketone bodies, these ketone bodies then through the blood circulation then these ketone bodies through the blood circulation go to the target tissues, and that tissue use ketone bodies as energy source. In that tissue, again ketone bodies enter into the TCA cycle, and through the TCA cycle, body generate ATP. So let's have a recap what we discussed up till now. That when the body is on the ketogenic diet, we take very low carbohydrate, we take very high fat, and we take moderate protein. In that case, both insulin level decrease, glucagon level increase, counter-regulatory hormones level increase. And that case, instead of storing fat, free fatty acids in the form of triglyceride in the adipose tissue, body start breaking down triglyceride present in the adipose tissue into the free fatty acids, and these free fatty acids then transported to all body tissues. But in the liver, a new thing happened. In the liver, that free fatty acid, instead of going into the TC cycle, that free fatty acid, after converting into the acetyl CoA, it will go into other cycle, that is the ketogenesis. And the body use ketone bodies. In that case, body use ketone bodies as an energy source, and ketone bodies are transported through the blood into the specific body tissues, and through TCA cycle, body use energy from the ketone bodies.